Okay, recording is started. So I'll turn things over to group 2 to present their CSD design.
All right, thank you so much. So good morning, everyone. And we are CUBE, short for Canisterized Unit Body Ejector LLC. We are group 2 in the mech design class. There we go. So just a brief overview of our itinerary. So first, we're going to meet CUBE and the people behind it. A brief overview of our hedgehog concept, some product overviews such as our subsystem, our key systems and features, and then our cost summary, and an overall summary of what we did and what we are, and then time for any questions you may possibly have. So pictured here are the engineers that worked on the project. It was a group of 6 of us. Additionally, we have background in the following companies that add to our legitimacy and our work done. As you can see, we have varied talents and varied performances. So definitely a good and reputable sources of grouping of individuals. So here you'll see our overall hedgehog concept. So streamlined CSDs for your one-of-a-kind CubeSat. So our passion lies in making aerospace research more accessible to people. Our economic probability is maintaining a low cost to appeal to broad audiences. And we're best at creating elegant solutions to mechanical aerospace design challenges. So a brief design overview. So here you'll see our full design with a transparent surrounding, so you can see all the features on the inside. So our communication system features a small and lightweight data port, able to easily interface with the equipment. Our door system is a fast opening system with high insulation. Our launch vehicle connection utilizes screw and foam to minimize vibrations. Our infrastructure is a square tube frame and utilizes rails to protect the CSD inside. Our ejection system is a spring-loaded launch. It is effective, lightweight, durable, and inexpensive. And our ventilation uses a check valve system for low potential for contamination overall. So here you'll just get a better look at some of the design overview. So you'll see a better standalone picture of our communication subsystem. There is our infrastructure as well as our door. So you could just see some of the components in better detail. And on the next slide, you can see the same thing for our ejection subsystem, our ventilation subsystem, as well as the launch vehicle connection means. So here are just some of our overall product dimensions in terms of the width, length, and height. So width, it stands at 10 inches, 10.8 inches. Our length is around 16.5 inches, and our height is 10.13 inches. I'll hand it over to Bailey.
I'll hand it back to Matthew.
Yes, this is our communication and power subsystem. And this is what we see here is a lower separation connector on the bottom connected to the CubeSat. It is a commercial off-the-shelf part. And along with the female DIL crimp housing, this is a connection to from the CubeSat, the CSD to the main launch vehicle, and the mount is made of 6061 aluminum. It is 1/8 by 1 inch. And then this meets our customer needs by providing a electrical grounding of less than 25 ohms, and all electronics wiring is grounded. We're through like 5.08 times 10 to the -3 ohms, and the total power, it meets the power requirements of the CSD, which is 10.5 watts, which is less than 12 watts, and the power supply, the max power supply to the CubeSat must be greater than 0 watts, and the power supplied by the disconnect wire is 45 watts. And the transmission power via communication to the satellite must be greater than 0.5 watts by the customer need, and transmission power by our Cube CSD is 20 watts. And this is a calculation of our analysis of our power supply. The power supply is the product of the amperage given by the manufacturer and the voltage of the system, which is 28 volts DC. And you see our calculation here, which is 140 watts. And this is a calculation of our electronic grounding and bonding, which is the product of the electrical resistivity of the ground rod by the length of the rod over its cross-sectional area. The classic resistivity of a wire calculation, and that is 5.8 times 10 to the negative 3 ohms. And this is our ejector subsystem, which is a stainless steel 302 spring. And then there's a base mount, which is 6061 aluminum sheet, and the spring pushing plate, which is nylon, as to prevent metal-to-metal contact with the CubeSat when ejecting it from the CSD. And this meets the customer needs by providing a initial velocity greater than 0.5 meters per second. The spring constant is 13.14 newtons per meter, so the final ejection velocity is 2.0 meters per second, which is good for our design. And it is able to maintain functionality throughout 12 months on Earth, and is able to provide a reasonable assurance for not contaminating the orbital space because all the polymers and lubricants are low outgassing components. And there's no like flying components for during ejection. And this satellite ejection final velocity or force is quantified by this spring constant of commercially available springs that we used, and the amount of distance the spring is compressed is calculated here. It's going to be 1.195.068 millimeters, and the spring force is going to be 256.309 newtons. And the frame and cover of the door subsystem is going to be 6061 aluminum rectangular tubing frame, and the sheet metal is going to be 0.032 inch thick, and there's melamine foam insulation in between these two aluminum sheets that thermally insulate and help with vibrational loads. And we have aluminum 5754 spring hinges that allow the door to open and close effectively, and a motor connected to a nylon latch that releases the door and allows the door to open underneath the CubeSat force pressing up on it by the spring. And this meets our customer needs. The capability number of components essential for the door function must be less than 20. And this door relies on one motor, so there's that number of components is lower. And the thermal environment minimum thermal resistivity was 0.5. And all our electronics can operate below negative 40 degrees Celsius, and the minimum operating temperature was 0 degrees Celsius. And the door reliability, the door can open within 0.5 seconds, and is reasonably assured to open underneath the required time length. This is a calculation of the analysis of the time to open the door, which is 8.4 seconds. This is the amount of time T for the door to fully open. And the thermal resistivity of the structural design is calculated using the adding together different resistivity coefficients of each material, which is the thickness and determined by the thickness and the resistivity coefficient of each material. And I'm going to hand it over to Bailey.
Very good. So next up, we're going to look at our ventilation subsystem. This is composed of 8 check valves, which are single flow inline check valves made of 316 stainless steel. They are 1/2-inch pipe size. So these are off-the-shelf components that will have the threaded ends that are used for connecting them to pipes cut off so that they can be narrower and be interference fit with the infrastructure. The check valves meet 2 of our customer needs, which are both liftoff and ascent venting and contamination protection. So according to NASA analysis, for the volume of our CSD, we needed a minimum of 0.783 centimeters squared of cross-sectional area for venting in a given direction. And we have a total check valve area of 1.26 centimeters squared going both directions, so inward and outward. I apologize if my dog starts whining as she's outside the door. The other thing that our system does is contamination protection, because our check valves are going to be covered with 5-micron mesh. So that prevents particles larger than 5 microns from entering in through the check valves when they do open. So just to show you a little bit of this ventilation analysis for calculation of the total cross-sectional vent area, you can see we have 4 vents facing in a given direction times their cross-sectional area is 1.3 centimeters squared facing each direction. And then if you plug that into the volumetric flow rate equation, you can see we have a maximum volumetric flow rate of air of about 5 times 10 to the minus 4 meters cubed per second, which is sufficient to depressurize the system and not risk bulging or anything on our CSD. All right, now for the infrastructure subsystem. It's composed, most of the structural support is provided by an external frame made of 6061 aluminum rectangular tubing that's 1/2-inch square with a 1/16 wall thickness. So those are the beams going around the major edges. There are also internal rails in the system, also made of 6061 aluminum, that are thinner, but they are attached to our outer frame by elastomeric profile dampeners, which serve to dampen shock and vibration. There is also the foam that we mentioned on the door inside the rest of the infrastructure to provide both thermal and acoustic insulation. And then the whole thing is clad in aluminum sheet metal to provide a little bit more stiffness and keep everything inside. So our infrastructure meets a bunch of our customer needs. It provides the structural load environment required, as well as addresses the shock load and acoustic loads that are put on the system. It conforms to the center of gravity requirements to fly on our launch vehicles, and it also has sufficient payload capacity to hold the 12U CubeSat that we need. So we can see that our frame by itself, without anything else in it, has a factor of safety that exceeds 5 under launch conditions. The internal dampeners isolate the CubeSat from infrastructure shock. Melamine foam reduces acoustic transmission by 95%, and then aluminum reduces it a little bit more, so that takes care of a lot of the acoustic load. We also know that melamine foam insulates thermally very well. The center of mass is 0.114 meters, which is below the cutoff height of 0.125 meters induced by NASA. and the payload volume is about 18,000 centimeters cubed, and what it needed to be was greater than 13,620 centimeters cubed to hold our CubeSat. So for our analysis, the maximum volume that could be contained in our infrastructure was slightly different than the maximum volume that could be in the CSD and enter and exit without hitting anything. So that maximum volume is about 15,000 centimeters cubed, which still exceeds the 13,000 some odd that it was required to be. And then the calculation of acoustic resistivity was found by taking the weighted average of noise reduction coefficients, which can be found for all the engineering materials that we used. So based on their thicknesses, the weighted acoustic resistivity was 0.828, which means that about 83% of the acoustic load on the CSD is not seen on the inside of the CSD. And finally, our launch vehicle connection subsystem. This is comprised of the base plate of the CSD. And then what you see there is a sheet of silicone rubber, which will sit underneath that base plate. And then it will be screwed to the launch vehicle connection mechanism with, I think it's 15 screws on the base plate. So you will have a CSD silicone launch vehicle connection sandwich. This takes care of a couple other customer needs, including the connection plane. Obviously, we needed to withstand the entire load being induced during launch and ascent, which is about 870 newtons. We exceeded that, and by our calculations, our launch vehicle connection can actually support about 200 kilonewtons. We also wanted to address the vibration environment of the CSD, so including that silicone in there dampens a lot of the LV, the launch vehicle vibrations transmitted to the CSD. And then finally, for our launch vehicle capability, our CSD mounting had to be compatible with whatever launch vehicle we wanted to put it on. So we wanted to use a minimal number of components, which could be easily changed. So our mounting screw locations are easily changed just by changing the screw hole pattern. For our analysis, we were calculating the shearing force that would be able to be withstood by the launch vehicle connection system to support a minimum of the force generated by the mass and the acceleration at launch and ascent. So the force required to be withstood, if you calculate it in pounds, is about 190 pounds. If you calculate the shear induced by that force, it comes out to be 630 psi. And based on the amount of force that could be withstood by those 15 screws and the, amount of shear that could be withstood by those screws and the amount of shear required, we have a factor of safety of 34.12, which is more than sufficient. So now we get to our cost summary. If you look at this pie chart, you can see a breakdown of our major costs for a production unit of the CSD. So you can see that 2,800 of almost 4,000 comes from off-the-shelf components, meaning a lot of what we're using is stock or pre-made components that we are combining to make a functional custom CSD. After that, $387 come from raw materials, $80 come from the energy required for assembly. Assembly itself requires $57, and then manufacturing composes $630. So as you can see, most of our cost is associated with OTS parts, and then a fourth comes from the rest of the requirements to put a unit together. And I believe with that, I'll hand it back to Claudia.
All right, so just some design highlights we really wanted to shine a light on that we really take pride in. So for starters, is the latch for our door release. So it makes for a simple yet effective release, and the design for it just allows it to come down smoother, not damaging the CSD in any way or preventing any major issues to occur in launch. So definitely something we wanted to take note of. Our check valves are definitely a unique ventilation system to help regulate pressure and contamination. Additionally, we have our dampening system that is featured on the infrastructure, and those help to minimize vibrations and shock and help overall protect our CubeSat, and it's how we were able to have such that high factor. And additionally, our spring plate for a controlled release, as you'll see, it has like an even base that applies an even amount of force to the entire CSD. So once it is released to launch off, you're getting that same application throughout the entire thing. There we go. So for prototyping for the next level in Mech 3, we strongly believe our design is ready for the next phase due to our key decisions. So not just our low cost for the value of the prototype, but also it proves to be effective, and the proof of concept and functionality behind our work, and also just testimonials from actual CSD models that we've seen and what we've done. We also just highly believe our concept is well thought out and is analyzed and ready for the next stage. In conclusion, why Cube? Cube caters to the user needs an effective and capable format. The CSD already exists. We didn't reinvent the wheel, but we made it efficient and affordable. Lower cost than current on the market CSDs, even with custom requests. It's definitely something we really wanted to take pride in. And our data supports our claims and effective use of the product. So before we move on, we'd like to have the question portion.
All right. Questions from our panelists? Uh-oh.
Oh, I guess I got something. So on one of those last slides you just had, there was something that said like shock absorption or vibration absorption. What exactly was that on the cube?
So if you look around the outside edge of that internal frame structure, those little black components are squished models of elastomeric dampeners. So that internal frame is what's actually in contact with the CubeSat. And then the frame is attached non-rigidly to this outer portion of the CSD. So that allows for a lot of vibration and shock mitigation because the vibration can't be transmitted through a rigid frame.
Okay.
And then we also have the, I guess, secondary, tertiary silicone rubber sheet between the launch vehicle connection components to further mitigate shock.
Okay. Awesome. Other questions? Okay, well then let me jump in then. So okay. You guys have those check valves on there. I might have missed it because I'm putting out fires on the side. But NASA has got, and I don't remember what the exact acronym is, but it's like MERV, something like that, which is, it's basically a number that's a ratio between the internal volume that you're trying to vent, and then the vent port size. And the number that NASA sets as the required ratio for that is it's something just over 5,000 centimeters. And it's not dimensionless because you're taking a volume and dividing by an area, so you're left with a unit of length. Did you spot that somewhere in the requirements for ventilation and calculate that for your vent versus volume?
Yes, so I think we found it with a different acronym, but Claudio, if you could go back to the ventilation customer needs slide. Based on our calculations with that ratio, we needed 0.783 centimeters squared of ventilation area. And we have not quite double that. And that's easily adjustable based on changing the orientation of the check valves. If for whatever reason a customer decided they wanted more ventilation area, that's only half, right? Because we had half to vent facing inwards and half to vent facing outwards. So if you needed to increase that area for whatever reason, you flip your other check valves around and call it a day.
Got it. Okay. Yeah. So, okay. So you guys have done that. And then, when this thing gets up into space, what's its anticipated steady state temperature?
Well, I was the one calculating that due to radiation in space, and the anticipated steady state temperature was around 77 degrees Fahrenheit.
77 Fahrenheit. Wow. Okay. That's like a nice spring day. Do you guys have a slide that shows where that temperature came from, like that calculation?
We do not on this presentation,
Got it. Okay.
but
Yeah.
the for the resistivity coefficient, that's on the one of the slides. It's but yeah, but no final temperature inside the CSD on this presentation.
I
Okay.
believe that was still in the works as something to be fleshed out this afternoon.
Got it. Okay. Yeah. The reason I ask, I didn't see it. And to be completely honest, every other group that has done a heat transfer calculation, I think have not done them correctly. So I wanted to just check on that to see. So I know we don't have a slide on it, and it sounds like you guys might still have a little work to do, but can you talk me through how you plan to do that calculation if it's not already done? Like, how do you get that steady state temperature?
Yes. Right now, we plan on getting that steady state temperature by getting the extreme temperature from the outside, heat flux from the outside space, and creating a resistivity circuit for the melamine foam and the aluminum, and then determining the heat flux inside the into the CSD using that resistivity circuit coefficients, and then by doing that we can determine the temperature inside the CSD.
Okay, I got you. So it's basically 1D resistor model is where you're going.
Yes, yeah, with
Okay.
the area of the radiation coming in from one side, going through the two plates, and then going inside the CSD.
Okay. Which is fine. That's actually more sophisticated than a lot of the heat transfer calculations I've seen. So that sounds good. I guess, how are you guys, because I've seen this mistake before, and I think I heard you say it. It sounds like you guys are planning to accept or absorb radiation. I think you said from space. Is that correct? And the reason I ask is because the CSD lives like inside a compartment inside the launch vehicle, right? So are you going to be exposed to space and be radiating to space? Or are you actually radiating to the walls of the launch vehicle?
We want to expect the worst case scenario. So if it can be exposed to space, it can be inside the launch vehicle capsule. So
Gotcha. Okay, so
just
that's
planning for worst case scenario.
yeah. Okay, so that's good, right? If you guys, presumably most of you have taken or are taking heat transfers, so you probably know or remember that it's sort of it's like a dark art, right? It's you never get the right answer, but you can sort of bound the right answer in heat transfer. So so if you're radiating to space, I think that's fine to give you, it'll ultimately be like a lower bound on the temperature. inside the CSD that the CubeSat experiences. But then what about the other extreme, right? So like the high temperature, you don't want it to get too hot either.
Yeah, we're planning on doing like analyzing both extremes. We just got more done on the lower extreme than the higher extreme so far.
Okay. Yeah, no, that's fair. There's like 12 more hours left, right? So like 10 more hours, so something like that. Plenty
I
of
think-
time.
That was also not our top analysis priority, just because the way that our aero design partnered group designed their CubeSat, they can compensate for temperature fluctuations themselves, like with their CubeSat standing alone. So ours is almost secondary protection.
Oh, okay. But now that's an interesting. So you guys, well, it depends on who taught your thermo class, but there's that classic thermo problem of you have an enclosed room and you open a refrigerator in an enclosed room, and does it get hotter or colder? Right. And you guys know it gets hotter, right? Which is sort of counterintuitive. At least until you do a first law analysis on the whole system and see where the energy is going. But if the CubeSat has its own, I'm imagining it's based on your description, it's active internal regulation of temperature. Where does the entropy go? Like they have to pass through the system like boundary of the CubeSat, right? To be able to reject entropy.
They're active and passive. So their active system doesn't get turned on until they leave the CSD. So it would be probably relying on the passive system. So like, and more insulation and thermal like paint coatings, which I'm not sure how much that would do while it's inside the CSD.
Okay. I'd be interested to see. So I'm with you. Like as soon as they launch, it's thermal management is basically their problem, right? Because your guys are out of the equation after they've launched out of the CSD. But like internally, passive thermal management has to be like thermal mass, right? Is really all you can do if you're not actively heating it. Well, I guess heating you can just sort of run electricity through a wire and get yourself hotter. So maybe that's what they're planning, is they're anticipating a cold environment and they're heating themselves to prevent getting too cold. So okay. I buy that. It's the other way, which sort of is off in the world of I can't imagine NASA would even allow this, would be some sort of phase change material. But that's a whole different nightmare. The other thing that I wanted to ask, and Bailey and I have talked about this kind of offline, is the selection. I think it's your communications and power system, the material selection. So I harped on this quite a bit. So I'll ask, when you guys made the selection for your like wires and cables and everything, how did you guys make that selection for the power and communication system?
Arthur, do you want to take that?
We haven't really necessarily went to depth of deciding the exact wire material that we're choosing. Something that was something to decide tonight as well. As to the plastic that's encompassing the wire itself, but what we did include within the material justification was also just the few parts, how it's going to be mounted to the system, how it's going to be connected, how the data ports can be connected to the overall infrastructure. That's more so what we covered within the material justification.
Got it. Okay. Sorry.
The wire that specifically connects between the CSD and the CubeSat was just taken from a supplier that our aero group gave to us. They said, this is the one that we're using, put it in your model. The rest of it, so the wire and actually the data port quick connectors were both from them. So the primary components.
Okay. So those were basically set by your customer / collaborator.
Yes.
Yeah. Okay. I mean, you know why I'm asking about this, right? Because we had that exchange about whether an Ashby plot was needed for a system where basically everything is predetermined. Um, okay. The other thing, just by way of sort of especially since we're on this slide, like way of compliments. I very much liked how well, and you guys did this, I think, for every subsystem. You walked through like what the customer needs were, what the quantitative metrics were, and then what the ultimate, functions were to demonstrate that you achieved all those customer needs. So, I'm like, this customer need map thing is like my thing, so I'm excited and happy to see it. But I appreciate that you guys did that for every subsystem, and you made it really clear that you're meeting all of the requirements. We've seen a few others where like I'm pretty sure that they met the requirements, but it like wasn't laid out as cleanly and clearly as this. So I appreciate you guys did that for all of your subsystems. And then the other thing that I really like that I've not seen anybody else do, you guys had that acoustic analysis, which I'm not sure if that's before or after this. Somewhere. Yeah.
That's the other time.
Yeah. So I need to look at this a little more to really understand it. So
the problem with this is that most of the way of calculating acoustic resistivity, or like the effective acoustic reduction, is to take a meter and go between two walls and probe it. There's not really a quantitative formula for it. So this was more of it is quantitative, but it's more of a qualitative approach to the analysis to try and determine the effective acoustic resistivity.
So is this like a technique that you guys found in a textbook or in the literature, or did you just kind of come up with this?
No, this was developed just by us. The noise reduction coefficients are published for all the materials that we use. But as far as we could find, there wasn't a method of doing like a acoustic circuit, for lack of a better term.
Yeah, no, that's exactly what this is, right? It's basically a Ohm's law type analogy for acoustic energy. And I'm maybe surprised but not shocked that you didn't find something else, because like sound and light are super weird. Light is also very like, because there's a huge element of it that's based on like human perception, right? So like, how loud something is, there's like an objective measure, and then there's sort of a subjective measure, and it's the subjective measure that actually seems to matter for measurement purposes. And so that subjective element is quite hard to capture. So again, maybe not super surprising that there isn't the equivalent of a acoustic circuit model floating around somewhere. But so I mean, I just, by way of an additional compliment, I mean, I think this is like exactly what engineers do, right? So I love this. Like, you guys couldn't find a textbook or a paper that told you how to do this, and so you took something that you knew was right from a different discipline, which is electrical circuits, and you applied it here to come up with this analysis, which I think is great. And I think you guys know this, right? The follow-on step, now that you've got this model, is to actually test it, right? Which of course we don't do that in Mech 2, right? Because it's all theoretical. Although next semester, when Dr. Prasad teaches, he's already talking about having students build prototypes in Mech 2, not in Mech 3. So that's coming. But so that would be the next step, right? Is now that you guys have got this model, you could actually build some test samples and instrument them and have a source of noise on one side and a microphone on the other side, and actually determine how good this model is. But I think just the kind of out of the box thinking that led to, hey, let's apply a circuit model to sound because we don't know any other way, I think is excellent. So I appreciate that you guys did this. And, even if it turns out to be wrong, this goes back to that, original thing that I said during the RER, right? Which is, if you don't know what to do something, right? So this, I think, is great. I don't know if any of you are thinking about, grad school, but you might imagine actually pursuing this as a master's thesis project, something like that, to see if this is valid. Because if there's no way of like predicting like sound intensity a priori in advance, we definitely need a model for that. So anyway, so I thought this was very good. So thanks for putting that together. Let's see, that's all I remember. I might have had a few more questions, but I didn't write them down. So I think I'm all set. Are there any other questions from Alex or Ria while we're here and we've got these guys?
I just wanted to say good job. I think I saw your guys's first design review, and you definitely improved on everything by a lot.
Thank you.
Cool. Okay. Sorry. There's louder than Bailey's dog is a couple of gentlemen doing some work on my house. So if you guys are hearing construction noises behind me, that's what that is. Okay. So I think we're good then. I think all questions have been asked and answered. And we were supposed to finish at 12:35, right? And we've got 8 minutes. That's never happened before. I've never finished either on time or early. So yeah, I guess there's a first time for everything. So this is probably a good time to wrap up then, since I think all the questions have been exhausted. So my kind of final comment is, depending on who you ask, either Mech 2 or Mech 3 is considered by at least the mechanical faculty in our department as the final boss in our curriculum. So John Brooks thinks it's Mech 2 and others think it's Mech 3. So at least from the perspective of some of our faculty, this is the most difficult, most time intensive class. So I just want to say that I really appreciate the energy and creativity and enthusiasm that you guys have brought to the class all semester. A couple of you guys have asked, some really challenging questions along the way that have made me think about, like, why do we do things the way that we do them? And maybe, we need to revisit, some elements of the class to further improve it. But I really appreciate that engagement and inquisitiveness and just the energy that you guys brought. So I want to just sort of say that in the recording so that you've got it for posterity. And looking forward to seeing your final design report to get these last few little bits, especially the heat transfer, all wrapped up so that we can see the final version of this design. But thank you for a great semester and for your patience with me this whole time.
Thank you. Yeah, thank you.
Thank you.
Thank you so much.
Very good. Okay. Well, this is your Zoom meeting, so I'll stop recording